So today we're going to learn about this partnership and most importantly the development of this flood monitoring system for the municipality of Rio de Janeiro in Brazil. Just give me... Yeah, so this partnership, the NASA Rio partnership, was initiated in 2015, over 10 years ago, with the overall goal of applying NASA observations to monitor, understand, and anticipate environmental hazards at the urban scale, particularly for the municipality of Rio. So since we've been pursuing this goal by conducting joint activities that leverage not only NASA products, but also, which is essential, local monitoring and crisis management capabilities. So initially, this partnership included hazards such as heavy rainfall, sea level rise, and landslides. But in the past 7 years, that was like in 2020, 2019, we started discussing the possibility of monitoring floods as well, taking advantage of NASA Goddard's unique modeling capabilities. Floods are very common in Rio and happens every summer, basically from November, December through March, April. Sometimes you can have like 2 or 3 major floods in the same year. For example, in 2019, there were 2 major floods in February and then in April that became world news back then. These floods killed several people and caused severe damage in the city. So this slide shows some photos and world news highlights from that year. But it's important to note here that these urban floods in Rio, they mainly arise as a result of storms combined with poor urban drainage rather than river and lake overflow. So the goal of this effort was, because it's been ongoing for a while, to transfer a customized flood monitoring system to local operations. And the proposed plan was the plan is to achieve combining NASA tools, models, and data sets, local expertise and monitoring capabilities, and capacity building. So we combine these three to get this tool transferred and in operations. And the Hydrological Science Lab at NASA Goddard Space Flight Center, we developed the Hydrological Modeling and Analysis Platform, or HIMAP, which is a global scale hydrodynamic model. HIMAP is included in the NASA Land Information System, or LIS, and within LIS is coupled with several land surface models. It has many other capabilities, including the assimilation of data from the Surface Water and Ocean Topography Mission, or SWOT, which is a new NASA CNES mission. The HIMAP can also represent multiple processes such as reservoir operation, water management, and urban drainage, which is a capability that was implemented to respond to the needs of this partnership. So the main challenge here was to represent fine resolution urban processes. Currently, that were back in the day, they were missing. They're generally missing in global river models, but it was missing, but not anymore in HIMAP. And that challenge required the development of an urban drainage module that I just mentioned. So basically, this module represents streets rather than rivers, and it also represents the water exchange between the street surface and groundwater drainage pipes, like we see in real urban drainage systems, as well as water storage and flow through the underground drainage network. And that representation is based on a series of parameters listed in the tables on the right. I'm not getting to details on these parameters, but Yeah, this schematic in the tables kind of, okay, I can answer the questions if anyone is more interested in this. So since I didn't have access to an urban drainage map, that information is not, and I think it is still, there wasn't, I think it still isn't available in the city. So these parameters had to be estimated based on our best knowledge, common sense. So an urban drainage map had to be generated through the acquisition and processing of local and satellite-based high-resolution information. And the resulting urban flood model covers a domain in the upper left map at 200-meter spatial resolution. A flood model can be as accurate as its inputs. And with that in mind, we gave special attention to the model parameterization. We used a LiDAR-based DEM, or digital elevation model, previously acquired by the municipality to represent topography across the city. And on the upper right here, we can see the fine resolution representation of buildings. Let me turn on my pointer. Not this laser pointer. Oh, here. All right. So this allows us to represent street flooding, for example. So if you know that where the building has a higher elevation, so the water won't be there. It will be in the lower elevation topography. So river geometry is also essential to represent flooding. The problem is that the municipality only had a handful of river and channel cross-section surveys across the city. So as a result, we had to be creative and use Google Earth, for example, to manually extract river and channel width at hundreds of locations and then spatially interpolate them. And finally, in order to determine where the urban drainage module would operate in HiMap, we used land cover maps to identify urban, rural, and vegetated areas, as well as the river network. And as a result of this, the area where the urban drainage module is operated in the model is defined the gray by the gray color in the bottom right map right here. So this means that wherever there is a gray, we have the urban drainage module, and where there isn't, where it's green, is just the regular model representing rivers and floodplains. These are either rural or forested areas. So the model was evaluated in terms of hourly water levels at 4 locations where the in-situ data is available during 3 flood events. So the flood events, the 3 flood events are represented by the columns here. So there's April 2010, and the other 2 events that I mentioned before, February 2019 and April 2019. And the 4 locations are each of these rows. So except for the top row, where there seems to be an issue with the river geometry parameterizations, because we can see that the peaks are represented, except that is the magnitude is an order of magnitude smaller. So it could be related to river width, misrepresentation. But the other 3, they represent the simulations show a general agreement with observation. You see the peaks are well represented, the timing as well. And we have to keep in mind here that the model was not calibrated. So a further calibration could even improve even more the results. All right, so here's some results for the flood event that occurred in April 2010. The top left animation shows hourly precipitation fields, and the bottom left animation shows water depth anomalies using the first time step of the event as the baseline. These results give us an idea of the magnitude of floods across the city and how they relate to precipitation. In order to extract more information from these model outputs, I developed this post-process downscaling algorithm that converts these maps at 200 meters to 10-meter spatial resolution, which is a DEM resolution. So the result is the animation on the right, showing the same event, but at the street scale. So here you can see the streets being flooded in Copacabana during that event, and many other neighborhoods in the city. So now that we have the model working, we combine these outputs with population data so we can quantify the flood exposure across the city. So based on three what-if scenarios with varying drainage systems, this means no drainage, the left column, optimal drainage in the center, and a constrained drainage on the right, we can map where and how many people are exposed to different levels of flooding. The top row shows the population exposed to water heights above 10 centimeters. So the shallow, just a mild flooding. Then the second row shows the population exposed to at least 25 meters. 25 centimeters. And then the following row is a half meter, and then the bottom row is a 1 meter or deeper. So this analysis could guide the municipality on where to prioritize improvements in drainage systems, for example. So we can see where the most exposed population is located. We can refine that analysis by dissecting the population data by ethnicity and income, for example. So the three maps here in the center of the slide show the distribution of minorities. And here minorities are defined as anyone self-declared as not white. The map in the center here shows the normalized household income, where one means the richest. That's as I said, normalized. So it's normalized for the city. Minimum maximum incomes within the municipality. And the third map shows the distribution of social infrastructure. That's what I call here the public schools and hospitals. So when we overlap the flood maps, those three flood maps from those three events with these maps here, minorities, income, and social infrastructure, we have some interesting results. But let's focus on the second and third row on the left, these two rows here. So they represent the fraction of minorities in normalized household impacted by different flooding levels. So as before, the flooding levels vary from 10 centimeters on the left side of the plot to 1 meter on the further right of each plot. So the three lines in each plot represent the what-if scenarios. So black is no drainage, blue is optimal drainage, and red is constrained drainage. So, but here in the second row, well, we can see that for any event and any what-if scenario, the fraction of exposed minorities increases with flood intensity. And similarly, household income drops with increasing flood intensity. So the deeper the flood is, the poorer the population, the poorer and more minority people will be located there. So these are striking, but somehow expected results, like empirically expected results. So this system can can show what was empirically known, but now we can give numbers to these facts. So the system has finally been transferred for operations as of April 2026. It took a long time because a lot of complications. The municipality was hacked, so this project was paused for 2-3 years.
1 minute.
Yeah, thank you. And it runs in near real time on AWS cloud with 15-minute updates. So every 15 minutes, it runs. It gives more this flood maps. It runs at 200 meter spatial resolution, as I mentioned before, and downscaled to 10 meters. So these features combined are ideal for flash flood monitoring, for example, that fine spatial resolution. It's forced with the precipitation from 33 gauges across the city and converts water elevation to flood severity index. So we don't use the actual model output to convert those model outputs to something that can be more easily interpreted by the municipality and the population. On the left side is a screenshot from the system as currently implemented with a view of flood severity index at 10-meter resolution. But there's still work to be done. One thing is the simplification of the flood severity levels, dropping from 7 to 3. 7, we decided back then is too much. Now 3, I think 3 is more ideal, just like informing no risk, moderate risk, and high risk. And the second thing is to extend the system to perform 1-2-day flood forecasts, which is the ultimate goal. And that's my last slide. I'd like to thank you for attention, and I'll be happy to answer any questions.
Thank you very much. If somebody has a quick question, feel free to raise your hand. I don't. Oh, I see one question from Aaron about, is the Rio FM model publicly available?
So that it's based on LIS. LIS is publicly available. So basically that's a customization of LIS and HiMap with local data, and that was transferred for operations. So the similar thing can be done for other locations, like if data is available. For example, NASA is funding us now to do the same thing for Hampton Roads in Virginia in the US. Yeah, so it basically be the first transfer of that idea, the methodology, to a US city.
And Marcelo has had one question. I don't know if you can answer that quickly about the different scenarios that you had.
Yeah, actually, I didn't provide details because the time was short. So those 3 scenarios of no drainage means that there is like just no drainage at all. Like there's no urban drainage. And then the optimal drainage means that whatever we assumed as optimal, and the constraint was like dividing by half the gutter size. For example, we kind of limited the sizes of the drainage system.